In today's class, we will learn the spiral curves. That is the last part of the curves. So what are the spiral curves? If a line rotates in a plane about one of its end, and if at the same time the point moves along a line continuously in a one direction, the curve traced out by the moving point is called the spiral. The point about which the line rotates is called as a pole. Okay, and the line joining any point on the curve with the pole is called as a radius vector, and the angle between this line and the line in its initial position is called the vectorial angle. Okay. Each complete revolution of the curve is termed as the convolution, and the spiral may make any number of convolutions before reaching the pole. So suppose this is your line, okay, and this line is moving about its one end, that is called as a pole. So this is your pole. So when the line is rotating, the point is moving around the line in a one direction. Then the curve traced out by this line is called as a spiral. Okay. So suppose when this line was moving about the pole, and suppose this is a spiral curve that is traced out by the line and a point, and when suppose this is a point and I am joining it with the pole, then this is your radius vector. The similar way, when the point is moved to this point, I am joining this point with the pole, then it is your radius vector. And the line was initially at this position only. When the line was started rotating. So the angle between these two radius vectors is called as a vectorial angle. Okay. So there are two types of spiral curves. One is the Archimedean spiral and second one is logarithmic spiral curves. So what are they? We will see. The Archimedean spiral curves is the curve that is traced out by a point moving in such a way that its movement towards or away from the pole is uniform, with the increase of a vectorial angle from the starting line. The use of this curve is made in a teeth profile of the helical gear and profiles of the cams. So it is also useful for the mechanical engineers. The second one is the logarithmic spiral curves. In the logarithmic spiral curves, the ratio of the length of the consecutive radius vectors enclosing equal angles is always constant. So when the radius is constant, means line is moving with the uniform velocity, but the point is moving in a geometric progression. Why? Because the ratio of the length of a consecutive radius are equal, while the angle between two radius vector was constant. Okay, so it is written here. In the other words, the value of the vectorial angles are in the arithmetic progression, and the corresponding values of the radius vector are in the geometric progression. The logarithmic spiral is also known as an equiangular spiral because of its property that the angle which the tangent at any point on the curve makes with the radius vector at that point is constant. Okay. So here is the some examples of the your trochoid curves and cycloidal curves. Okay. So here you can see it is your shaft, and how it works, it is shown here. See, it is your eccentric shaft. Okay, this is your cycloidal disc. This is your output shaft and pins and wheels. So how they are moving? So this is your epitrochoidal curve. The outer side, at the outside, when the disc was rotating, that is making the trochoidal curve. Or you can say that where this is your epitrochoidal curve. Okay. What it is mean epitrochoidal curve? When the point is outside of the curve. Okay. So this is your parts of the shaft. This is your outer pin and ring gear housing. This is your inner shaft. These are the inner pins. Okay, this the whole assembly is showing here how they are connecting to each other. This is your output shaft. So this is your whole assembly, and you can see here how the shaft is moving with the help of, here you can see here in the 3D diagram also how the each part is moving using the sacroidal curves, epitrochoidal curves, right? Here you can see gear trains. So this is using the your concept of the involute. Using that, they are moving. Here you can see also they are also using the involute concept of involute, the whole gear and helical gears. These are the planetary gears. This is your pulley and belt, and this is your harmonic drive. So I am not going into the details, but you should know where the curves can be used. So in this video lecture, we will learn the how to draw the curves. The first one is the ellipse deck, and the method is called focus method, or you can also say it is the general method of drawing. So see, it is your directrix, and the distance between directrix and focus is given as a 50 mm. So you can easily mark the focus on the axis F1, that is 50 mm away from the R1. After marking the F1, eccentricity is given is your eccentricity is given is the 2 by 3, means it is the ellipse. Eccentricity is less than 1, so it is the ellipse. If the eccentricity is given, you can easily mark the point V1. Okay, so this distance will be 20 mm, and this distance will be 30 mm. Okay, after marking the point V1, what I will do is I will draw a perpendicular from the point V1. Okay, and I will cut an arc on this vertical line having the length of V1 F1. means this distance is nothing but the 20 mm. So like this I can cut a mark by a rounder here on the vertical line. Okay, after marking the point, this is your Q, I will draw a straight line that will pass through R1 like this. Okay, so in this line actually if you take any point on this line and draw a perpendicular, so this perpendicular distance and this is the horizontal distance, the ratio will be nothing but 2 by 3 from the similar triangles. Okay, so using this uh, ratio 2 by 3 ratio, we will draw all the points on the curve. See, this is your point V1, this is your point on the curve. Okay, for that I will take some random points on the axis on the right side of the V1. Okay, this distance of the point can be random. Okay, then I will draw the perpendicular lines from each and every points. After drawing the vertical line, okay, what I will do is I will take an arc length of A1, this is your first point. So I will take a arc length of A1, I will put the rounder on a F1 and then I will cut an arc on the line A1. Okay, so what will happen is you will get a point, your first point P1 on the ellipse. So how can you say this is a point on the ellipse? See, here you can see this distance is nothing but the distance A1. Okay, and if you take the horizontal distance from the directrix, it is nothing but the R1 1. This is your horizontal distance of this point. So the ratio will be nothing but the 2 by 3. How? You can see this is your P1 F1. P1 F1 you can write as the A1 and this is your P1 M. So you can write it as the R1 1. Right? So and A1 V1 and R1 1 is nothing but the 2 by 3. The similar way you can mark other points of the curve on these vertical lines. So in this, it is the second line. So in this line you will take a distance of F1B and you put the rounder of F1 and mark it on the vertical line. You will get the same point as the B, right? So this is your point P2. Then it is your third line. You will take a distance C3. You will put the rounder on F1 and you will mark a point on this line having a arc length of C3. Okay, the similar way you can find the other points, right? So it is another example D4. Like so, the similar way you can also mark the points below the axis. After that, there will be some point. Okay, so suppose this is your line, another line, and you mark the point, you measure the length, you put the rounder on F1 and you mark the arc. Then there will be some line when your rounder will not reach up to that point. It will cut on the axis. Whenever that happens, it is your vertex V2. Okay, after that you can join all the points either by freehand drawing, or what you can do is you can join all the points with the help of a French curves. How? whenever you use the French curve, you should take at least 3 to 4 points joining at once with the help of French curve. So suppose you are starting from the here, you put the French curve, that is 3 points means V1, P1, P2 at least should be on the periphery of the French curve, and if there is a more points, that will be a good, that will be good. And after that, when you joining the other points, so you should take some portion that you have already marked. Means if you take 3 points means up to here, then for drawing other parts you should start from here. So P1, when you're drawing the other parts, so this portion P1, P2 should be there on the French curve, then you can mark the other points. When you're using the French curve, you cannot have all the points at once. Okay, only 3 to 4 points will be there on the periphery of the French curve. So in this way you can use the French curves. After you have to means join other portion as well, so you have to complete the drawing. After that, suppose I want to draw a tangent and normal on any point that is on the ellipse. So it is a point S and I want to draw tangent normal at this point. So what I will do is first I will join this point with the focus. Then I will draw perpendicular to this line that will cut directrix at any point. So suppose this is a point T. Okay. So after getting the point T, I will join the point T and S. Okay, so this will be your tangent and you can draw the perpendicular to it. That will be the normal. Okay, so this is the general method and you can use this method to draw the parabola as well as your hyperbola. Okay, the same method you can use. And there are some other method as well, but those are not in your course, so I will not discuss those. See, in the whole process, what we want to do is we want to draw the ellipse and tangent and normal. So except ellipse and tangent and normal, all these works are the construction work. So you have to draw all other things with the help of a 2H pencil, and ellipse, tangent and normal, and also you can draw the axis and directrix with the help of a HB pencil. And other thing will be you have to draw it with the help of a 2H pencil. So there was another curve that was cycloid. So how can you draw the cycloid? Suppose the problem is given that draw a locus of a point on the periphery of the circle which rolls on a straight line. Take circle diameter as a 50 mm. Okay, so you have to draw a cycloid, right? So first you draw the straight line and a circle having a diameter of 50 mm. After doing that, okay, you have to cut this circle into the at least 8 parts, or you and also you can divide it into the 12 parts. See, there will be more points. If there will be more points, your curve will be smooth. If there is a less number of points, then your curve will not be that smooth. Okay, however, you will get the cycloid curve. So at least there should be at least 8 points, and if you cut it on 12 parts, that will be good. Okay, to circle, and you want to cut it into the 8 equal parts, that you can do it very easily, right? First you can divide it into the 4 equal parts. Then you can draw the line at the 45 degree. Suppose now you want to cut it into the 12 equal parts. So either what you can do is either you can draw the line at the 30 degree and 60 degree, then 120 degree and 150 degree. Or there is another way that is very easy, that you can take an arc length of a radius of the circle, then you can cut an arc on the circle. Okay, so this point, if you join with the center, give you the angle 60 degree. The same way you can cut the arc from the here, so you will get the angle. If you join this point with the center, then you will get the 30 degree angle. Okay, the similar way you can cut the other parts. So I am cutting it into the 8 parts right now, and suppose now your circle rotates and it completes one round. Means if circle rolls one round, means suppose this is your point and you want to trace the path of this point. So if circles complete one complete round, then this point will come again to this position, right? And the distance covered by this circle will be nothing but the pi d, right? So if dividing the circle into the 8 equal parts, then I have to cut, or you can say divide, the pi d length into the 8 equal parts. So I am naming the points like 1 2 3 4, okay, 7. This is your point P. Okay, this is your distance pi d. So I have to cut pi d distance into the 8 equal parts. If you cut the circle into 12 equal parts, then you have to cut the pi d distance into the 12 equal parts. Okay, now suppose your circle is moving 1.5 round, then the distance covered by this circle will be nothing but the 3 by 2 pi by d, right? 3 by 2 pi d. So if I am cutting the circle into the 8 equal parts, then I have to cut again pi d distance into 8 equal parts, and there will be another half pi d. Those portion I have to cut into the 4 equal parts, right? So remember this, if you are cutting the circle, means you are cutting the pi d distance into the 8 equal parts. After that, I am marking these points also as the 1 2 3 4 5 6 7, and this point will be nothing but the P. So now suppose your circle is moving. When the circle is moving, your center point will move on this straight line, right? So suppose your circle is moved 1/8 round, means your circle is now here, right? So the center point will be nothing but here, and this point P will move at this position, right? So what I will do is I will mark the center point first here. When the circle is moving 1/8, then I am marking a center. Your center will be moved nothing but the here. So I am marking these center points when the circle is moving as the C1, C2, C3, C4, C5, C6, C7 and C8. Okay, so as I just told you, your point will move here, okay, and the distance of the point P from the center is nothing but the radius r. So to trace the path of a point P, what I will do is I will draw the horizontal line from the 1, 2, 3, 4, 5, 6, 7. Okay, and when I will draw the horizontal lines, so you can see your point 1 and point 7 is passing through the same horizontal line. Okay, 2 and 4 passing through the same horizontal line. Your point 3 and 5 is passing through the same horizontal line, and this is the from the point 4. Okay, so when the circle is moved from here to here, your center is now here, and from the center distance of a point P is nothing but the r. So I will take the rounder, put it here, and I will cut an arc of length r at this horizontal line. So I will get the position of point P when circle moves. Okay, so this is your first position of point P. Similarly, now your circle has moved here, then I will put the rounder at C2 and I will cut an arc of a length r on this line, this horizontal line. Then C3, then C4. After that, okay, so here you can see I am cutting the points on the left hand side because your point P is moving left hand side. After that, after the point 4, your point P is moving here. That is the right side of the center. So from C5, I will cut the arc on the right side of the center. Like that. Then C6, C7 and C8. So when the circle is moved to the C8, your point will be again on this horizontal line. So after getting all the points, I will first mark all the points P1, P2, P3, P4, P7 and P8. Then I will join all the points with the help of a French curve. Or also you can draw it freehand. You can also do the freehand drawing. Okay. So see, whatever I have just discussed with you, like scale, circle, cycloids, cycloidal curve, parabola, ellipse. See, on all these drawings, naming are important. In a scale, whenever you are cutting the arc, there should be names like 1, 2, 3, 4, 5, 6. Okay. In a parabola also, ellipse also, there will be a proper naming. Okay. So here also, you have to draw cycloids with the help of a HB pencil, and all the other work you have to draw with the help of a 2H pencil. Now the another example is superior trochoid. So here the problem is given: the draw locus of a point 5 mm away from the periphery of a circle which rolls on a straight line path. Take the circle diameter as the 50 mm. So again, there is a 50 mm diameter is given. This is your straight line, and the point is 5 mm away from the periphery of the circle. This is your periphery of the circle. This distance is nothing but the 5 mm. So from the center, it is nothing but the 30 mm. Okay. So for drawing this, okay, the whole process is same, except there is a one change. Okay. What is that? See, this is your circle. So your circle is moving. So this distance will be nothing but the pi d. okay, and diameter is nothing but the 50 mm. So this distance will be, okay, you can calculate. But the point is moving according to this big circle, right? Your point is here. When the circle is moved 1/8 round, your point will be here, right? So for that, what I will do is I will draw the horizontal line from these points. This is your 1, this is your 7. There will be one horizontal line passing through 1 and 7. There will be one horizontal line passing to 2 and 6. There will be one horizontal line passing through 3 and 4. 3 and 5. And there will be one horizontal line from the 4. Right? And when the circle is moved from C to C1, right, I will take arc length of 30 mm. Now it is 25 plus 5, 30 mm, and I will cut an arc on this horizontal line of 30 mm. The similar way, I will cut all the points from all the circles, center points, and you will get all the points. After that, I will join them with the help of a French curve. Okay. So this is your superior trochoid. The same way, there is an interior or inferior trochoid. So this is your circle, and this time your circle is 5 mm inside the periphery of the circle. So this distance is nothing but 20 mm. Now you will cut. First, you have to draw all the horizontal line from circle that is inside, and you have to cut the arc having the length of the 20 mm from the center points. So you will get all these points and you can draw it. Okay. So now the method of drawing tangent and normal for the cycloid. So we have drawn the cycloid. Now you have to draw the normal and tangent. So suppose there is a point is given. I have to draw the normal and tangent at this point. So first I will find the center for this point. How? You know the radius of the circle. You take the arc length of R and cut on the center point. So that you will get the center point for the point Q. After that, I will draw a normal on the horizontal line and I will get a point N. Then I will join point N to the Q. So this is your nothing but the normal, and perpendicular to it you will get the tangent for the cycloid. Okay, now this is the question for the epicycloid. Draw locus of a point on the periphery of circle which rolls on a curved path. See, in the previous problems, circle was moving on the straight line. So that was the cycloid. When circle is moving on the curved path and it rolls outside the circle, it is called as a epicycloid. When it rolls inside the curve, then it will called as a hypocycloid. Okay, so this is the example of the epicycloid. Take the diameter of the circle is 50 mm and radius of the directing circle on which the circle will move. Okay, that diameter is 75 mm. So first I will draw the 75 mm, taking the radius of the directing circle is 75 mm. So this is your 75 mm and I will draw an arc. After that, I will put this circle that will be having the diameter of the 50 mm. Okay, so this is your circle. So now your circle is moving around this curve. and completing the one revolution. So the distance covered by this circle will be nothing but the pi d. So suppose you are taking the diameter of the small circle as a small d, and the radius of the your directing circle is capital R, or capital diameter is capital D. Okay, so how will you mark that distance from this curve? See, the distance that I know is the 2 pi r if it is a small r, if you take, okay, and this the length of this whole circle will be nothing but the 2 pi r, right? The perimeter of the big circle will be 2 pi capital R. So if you take the ratio, you will get the angle. So okay, I will come to that. Before that, okay, just as we do in the previous problems, I have to cut the circle into the 8 equal parts. Okay, after cutting the circle into the 8 equal parts, in the earlier problems we have drawn the horizontal line. Now we have to draw the curve when you are drawing the epicycloid or hypocycloid. So this is your center point O, this is your radius R plus diameter, means 175. So you will take the radius of 175 and you have to draw the n arc. The similar way you have to draw the arcs that will pass through 3 and 5, 2 and 6, you center point 1 and 7. Okay, so and here you can see this angle you are getting r by 2 pi r divided by 2 pi r. So 2 pi is cancel out. So it will be small r divided by capital R into 360 degree. You will get the theta angle. Okay. So after that you have to draw the horizontal arcs, and also if you are cutting 8 equal parts, you have to cut this angle into the 8 equal parts. So suppose your angle is 80 degree, so the angles will be 10 degree, right? Or you can also divide it by using the bisecting method. Like you have to put the rounder here and you are marking the some arc here, then you put the rounder here and mark the arc here, then you will get some point, and that point you can join with the O and extend up to the your last curve. Okay, so like that you can you can divide the angles, or also you can do it with the help by measuring the angles. Okay, so this is how you have to cut the arc into the 8 equal parts. So now you have to draw the arcs that is passing through the center point. This arc is passing through the point 3 and 5. Then this is passing, not passing it here, but when you draw it on this sheet, then you will see this arc will pass through point 2 and point 6. Then another arc you have to draw that will pass through the 1 and 7. Thus now the same, you have to follow the same procedure. So on the center line you can mark the point C1, C2, C3, C4, C5 up to the C8. And now you have to cut the arc on the first arc that is passing through the 1 and 7, right, on the left side of the circle, center point. And this arc length is nothing but the radius r, that is a 25 mm. The similar way you can mark all these points and you can join you can join all these points with the help of a French curve. So this is your epicycloid. The similar way you can also draw the hypocycloid. This is your same question, but the circle is moving inside the directing circle. The only difference is that. So the procedure is same. Okay. So now you can see here your circle is moving in that direction. Okay. So your point 1 will be here. 2, 3, 4, 5, 6, 7. Okay. Your direction of the circle is anti-clockwise. So it is the same procedure. Okay. So you can get the hypocycloid. Now the involute of the circle. So suppose it is a circle having a diameter of 50 mm. It is not given here. You can take the 50 mm. 50 mm. Okay. So as we did in the cycloid and hypocycloid, epicycloid, here also we have to cut this circle into the 8 equal parts. Okay. So suppose your string is fixed at this point and it is unwounded. So we have to wound this string around the circle. So and this string is having the length of pi d. Okay, that is equal to nothing but the perimeter of the circle. So as I have divided the circle into the 8 equal parts, I will divide this line into the 8 equal parts, and also the dividing this line into the 8 equal parts as we did in the scale. Okay, the same procedure we have to follow. So this is the points. Okay, after that what I will do is I will draw the tangents from all these points 1, 2, 3, 4, 5, 6, 7 tangents. After drawing tangents, what I will do is suppose when I am wounding the string around the circle, okay, so this one point will touch here, then the remaining portion will be nothing but the having the length of the 1 to 8, right? So this distance you can mark it from the here, you put the rounder here, and on the straight line you can cut an arc having the length of 1 to 8. Okay, or 1 to P. This is a point P, so here it is written as a P. So this is your way. When you want the string up to here, then your point 2 will touch to the point 2 on this circle. Then the remaining length will be nothing but the 2 to P. You can again take the rounder, okay, and take this distance. You can then you will put the rounder on the point 2 on the circle, and you can mark the point P2 having a length of 2 to P. The similar way you can do with all the points, and you will get all the points of the involute. like P3, P4, P5, P6, P7, and after that you will get the point P8 at the point 8 on the circle. After that, I will join all the points with the help of French curve. See, here the involute is the main part that you have to draw. And the other thing is the construction work. So, accept the involute. This is your involute. So, accept the involute, all the other drawing will be of a 2H pencil, and only the involute part will be made of the HB pencil. Right? So in this diagram, actually, it is not means taking those into the account, but you have to take care of these minor things when you are drawing the when you're drawing anything on the sheet. And also, you don't have to mark, you don't have to write these things like 1 to P, 2 to P, 3 to P on the drawing sheets. Okay, this distance you don't have to write. So now, how will you draw the normal and tangent to the involute? So suppose we have already drawn the involute, and this is the point where you have to draw the tangent and normal. So first of all, I will join this point with the center C like this. Then I will draw the semicircle. Okay. So this is your outermost point Q and C, and this is your semicircle. So you have to find out the center, and you can draw it very easily. After that, whenever this semicircle is cutting this circle, okay, from that point you have to join the point Q. So this is your normal, and perpendicular to it, it will be your normal to the involute. So now you have to draw the involute of a circle, and the string length is more than pi d. Okay. So again, you can take the 50 mm diameter for the drawing the involute, and again I will dividing it into the 8 equal parts. Okay. And again I am winding the string. So up to the, so this is your string length, that is a 165 mm, that is more than the pi d. Okay, so when you are winding the string, okay, so this is your first point that will touch here. The remaining length will be nothing but the 1 to P, right? This is the same procedure. So you will follow the same procedure, and at the end, on this line, okay, when you are winding it, your point P will be somewhere here. So the remaining length will be nothing but the 8P, right? But your question will be completed when this point P will touch the circle. You have to wound the string completely. Okay, so how will you decide that this point, where it will touch on this circle? Because you cannot take the measurement on the curved portion. Okay, so for that, what I will do is I will draw a chord that will join the point 8 and point 1. Okay, and suppose uh, this distance is nothing but the pi d divided by 8. Okay, so suppose it is coming out to be a 10 mm, and the remaining portion is suppose your 1 mm. Okay, for example, it is coming out to be 1 mm, this remaining portion. So it is nothing but the 1/10 of this measurement. So what I will do is I will divide this portion into the 10 equal parts. Okay, for example, this length is coming out to be a 8 mm. Okay, so I will take the 1/10 of the 8 mm. Okay, that will be a just less than the 1 mm. So you cannot measure that. So you can just mark the 1 mm on the chord, and you can draw a line passing through that point up to the up to this circle. So this is how you can get the point where this point P will touch on the circle. Okay, or if you know any other methods to do that, you can also do it with that method. Then again, if your string length is less than pi d, so the same process you have to follow as we did in the previous question. So this time the length is less than that point. Okay, so this is how I will do it. Okay, so this is a point P. Okay, so here it is a simple process you can follow, 1 to P, 2 to P, okay, up to the 7 to P. After that, you have to follow the same method as I told you in the previous problem. Okay, you can draw the chord 7 to 8, and you can divide the chord according to the whatever portion you are getting to the 7 to P, and you can complete your drawing. So in the next problem, we have to draw a spiral of one convolution. Taking the distance to P to O is the 40 mm, means P is the point and O is the pole. So the distance of a point from the pole is 40 mm, and we have to draw a spiral of a one convolution, means the point is reaching toward the pole by completing one convolution. Okay, so the first thing what we have to do is first we have to draw a circle having a radius of a 40 mm. Then we divide the circle into the 8 equal parts or 12 equal parts as I have mentioned in the previous problems. After that, see, in this spiral what happens, the point moves along a line while the line also rotates about the pole at the same velocity, right? So suppose your line moves 30 degree, then the point will move 1/8 of 40 mm, right? So because of that, what we will do, we divide the line into the 8 equal parts because we have divided the circle into the 8 equal parts. So now your point is here and this is your point O. Line is moved to the position 1, O1, then your point will move to this position. So what I will do is I will take a arc of O1 and mark on this line. The similar way, when the line moved to the position 2, then I will take a arc length of O2 and I will mark on this line. The similar way I will do with for the every position of the point, and I will get the spiral curve. And at the end I can join with the help of a French curve, or also you can do the freehand drawing. So in the next question there is a 2 convolution. So now your point is 80 mm away from the O and it starts moving toward O, reaches it in 2 revolution around it. Draw locus of a point P. So first I will draw the point P and point O 80 mm apart, and I will divide the line PO into the 16 equal parts. If I am dividing the circle into the 8 equal parts, then I have to divide PO line into the 16 equal parts. And the same procedure is same. So when the point is your line is moved to 30 degree, then your point will move to the position 1. This is your position 1, this is your 2, this is your 3, and this is your last position. So like this, I will draw all the points of the spiral curve and the 2 convolution, the point is reaching toward the point O. So this is the method for drawing the tangent normal to the spiral curve. So the spiral curve we have already drawn. So for that, what you have to do is suppose this is a point Q where you have to draw the tangent normal. So there is a term constant of the curve for the spiral curves, that is nothing but the difference in the length of the radius vectors divided by angle between the corresponding radius vector. Okay, so this is your point OP, your line OP. This is suppose your point is moved to the P2 point, then this is your another radius vector. So that the difference divided by the angle between them, that is nothing but the pi by 2. So you will get the constant of the curve 3.185 mm. So after getting the constant of the curve, you have to draw a circle taking the center as a O. After drawing the circle, you have to draw the tangent from the point Q on this circle. So that will be normal to the spiral curve, and perpendicular to it, you will get the tangent to the spiral curve. So here is the next problem in which you have to draw the logarithmic spiral that is having the shortest radius of 40 mm and the length of adjacent radius vector enclosing 30 degree are in the ratio of 9 by 8. Okay, what that means is when the line moves 30 degree, then your point moves in the ratio of 9 by 8 from the pole. Means, so the length of the first radius vector was nothing but the 40 mm. Then ratio of radius vector is given as a 9 by 8, means the length of the next radius vector is nothing but the 9 by 8 into the 40 mm. That will gives you the 45 mm length. Means your point is moved from 40 mm to the 45 mm from the pole, right? And you have to construct the spiral of one revolution. So for that, first you have to construct the logarithmic scale. Why? Because as you are getting the next radius vector length is 45 mm, when you are multiplying it with the 40 mm, for the next radius vector again you have to multiply 9 by 8 with 45 mm. That from that you will not get the integer value like you are getting the 40 mm, 45 mm. So for that, if you draw a logarithmic scale, then you don't have to do the calculation, and also you will get the right length of the radius vector. How will you construct the logarithmic scale? For that, first you have to draw two straight lines OA and OB at a 30-degree at the angle of 30 degree like this. Then first you have to mark the point P on OA, that is 40 mm away from the O. Then you have to mark the point P1 on OB, that is nothing but the having the length of 45 mm. Then you have to cut an arc. Before that you have to join the point P with P1. Then you have to cut an arc having the length of OP1 on the line OA. So basically you are getting the point P1 on the OA. Then you have to draw a parallel line to the PP1 so that you will get the another point P2 on the line OB. So this is your nothing but the, so that is nothing but the you are getting the length of the your third radius vector, or you can say the second point. You can get the another point like P3, P4, and so on up to the point P12. After constructing the logarithmic scale, okay, you first have to draw the circle and divide it into the 12 equal parts, or also you can draw the 12 lines. Those are having the angle of 30 degree with respect to each other. Then I will just first mark the point P on the first line, that is nothing but the 40 mm away from the 40 mm away from the pole O. So now you can mark the point P1 having a length of OP1 on the first line like this. The similar way you can mark the all other points like P2, P3, P4, measuring the distance from the logarithmic scale, and you will get all the points of the logarithmic spiral. Then at the end you can join all the points with the help of a French curve or by freehand drawing. Very much for your kind attention, and in the next class we will start the projection.